Okay, the recording has started. The stage is yours.
Thank you, Sonar. Good afternoon to everyone. That was the point that I stopped yesterday. It was about the quasi-normal modes. First of all, I briefly introduce what are those. First of all, these modes are nothing but the energy dissipation of a perturbed field or object. Maybe before the quasi-normal modes, we have to remember the normal modes that we see in classical mechanics. For instance, when you perturb a wine glass with a knife, we hear, the sound because the glass will start to ring, and it rings with a superposition of its natural frequencies. And if you are also the outside of the, let's say, the room that we made this experiment, I mean, the glass ringing, you can recognize that this sound is belonging to the glass by just hearing its sound, because those frequencies are just belonging to the glass. The similar experiments can be extended to metal, wood, and etc. So once you have a table of the normal modes recorded in your brain, whenever you hear the sounds, although you don't see them, however, that is a good detection method. Once your brain compares the sound detected by your ear and matching it with its own table, let's say there's a natural frequencies table that we experience while living in this earth, and we automatically recognize which ring belongs to which material. So the same analogy can be extended to the black holes. So when a black hole is perturbed, it will also ring with its own characteristic frequencies. Again, the question is, okay, suppose that this black hole is ringing and we are detecting its natural frequencies, but what type of black hole we have, although we didn't see it. So this is also the future agenda of astrophysicists observers. And now the LIGO made the gravitational wave detection show that the gravitational wave detection is also possible. But in the future, maybe with high-tech equipments, we can get the tables of different black holes. Each one will have its own characteristic frequencies, and these characteristic frequencies can give us information about what type of black hole we are going to observe. So in this regard, the quasi-normal modes are very important. So, but the main difference of the quasi-normal modes from the normal modes, the quasi-normal modes will belong to the gravitational waves. This is one part. The second part is their amplitude should decay in time, okay, like this oscillator waves. This is what I shown here. You see, it's not just exponential decay, it will oscillatorily decay in time. So how it is possible? So if we have a quasi-normal mode ringing, its frequencies should be complex. Okay, so it should have a real part which indicates oscillation, and it must have a imaginary part which shows exponential decay. In particular, it must have imaginary part. Okay, because it must decay in time. That is the compulsory condition or the must condition for the quasi-normal modes.
Can I ask
Yes.
a question?
Sure, Ahmed.
Can you go back to the figure, please?
Sure. Yes.
So if the oscillation decay in time, then we call it quasi-normal modes. Just a question. Is there any oscillation that do not decay in time? They will keep the same forever?
This is possible. If instead of decaying time, it may grow in time. And this is called black hole bump. That indicates instability. That indicates that the black hole will be terminated. And this is another, of course, the subject in physics. And if you just Google it, you will see that there are many also papers on black hole bump. One of the best scientists also is in Turkey, Ephraim. Most probably you hear his name. He has also good works on the black hole bumps. But detection of the black hole bumps nowadays, it's not in the agenda of astrophysicists. Instead of they are looking for the quasi-normal modes, which seems more realistic comparing with the black hole bump. So it is possible, surely. But that is not the quasi-normal modes. The quasi-normal modes should be the ones should decay in time by making oscillation.
Okay, thank you.
Okay, so therefore the amplitude of the oscillation, here it is going to be our scalar field. It will be, of course, in a plane wave structure. However, this frequency, omega, should be in a complex form. Therefore, we will have one real part, which is going to be oscillator mode, and we will also have damping mode, which is denoted by omega I, and it is going to be the frequency of the exponential mode. So our quasi-normal mode frequencies is expected to be formed in complex form. Okay, so as I mentioned before, it is believed that the quasi-normal mode of a black hole is a characteristic wave, and it will lead to the direct identification of the black hole existence through the gravitational wave observation. If it will be realized in the future, I mean the direct detection of the gravitational waves, because the LIGO, what they detected, the merging of two black holes, and not their direct detection is made, only that length contraction in the observatory, which is in the L shape, was detected, and they deduced that, they publish it that, okay, this is the gravitational wave. However, there is currently, we don't have any device to directly identify the gravitational waves, and still it's a big question standing on the scientists. Anyway, but at the end of the day, to have the quasi-normal modes, we need perturbation. And so the bosses of the quasi-normal mode subject are Subramanian Chandrasekhar and that Wheeler. And later on, Kokotas and Schmidt also, they became very popular in these subjects. So I suggest the listeners and the students to have a look at their books and articles, and you can get more information about those quasi-normal modes. But so I am going to show how we can get those quasi-normal modes in analytic way. To have this, again, I am going to use one of the instructive example for the massless and bosonic perturbations in rotating linear dilaton black hole, because we already got its exact solution, if you remember, in our previous lectures. But what are the boundary conditions? The quasi-normal modes are defined as the modes with purely ingoing wave at the horizon and the purely outgoing wave at the spatial infinity. While I am teaching this subject to students, I make one simple analogy, because at the end of the day, it is considered as a ring. So if we have, sorry, just let me plug my pen. So if I have a black hole, and assume that here we have an observer, which is at the spatial infinity. Suppose that here you have a guitar string, and we are now perturbing the string. So what will happen when you perturb it? You will observe it will make a sound, and the waves will go in to the black hole, and the other wave will go to spatial infinity as outgoing wave. So these are actually the boundary conditions of the quasi-normal modes. At the event horizon, we will have just pure ingoing. At the spatial infinity, we will have just pure outgoing. And when we apply these boundary conditions, you will see that those lead us to find what are the frequencies of such modes. Okay, so this is important, and they will appear in the structure of quasi-normal mode frequencies. Anyway, so this is just an analogical, it's here all the time. Anyway, the solution that I'm going to assert, as I mentioned before, it was belonging to that rotating black hole. We analyzed it before in many times. It's a rotating one because we have here a cross term, you see. This part shows that we have, because at the end of the day, you will have this cross term. So which means the rotation, okay? So we will have a rotational black hole. It's just an example, rotating linear dilaton black holes. So it has double horizons because of this rotation. So we solved the massless wave, scalar wave, and we got this hypergeometric solution. In this solution, this eta is very important because it is related with the frequency, and we will use it. And this eta also determines whether I have ingoing or outgoing waves. Anyway, so this is my condition, and in this condition, this is my general solution, and I have to now impose one of my condition to that solution. We should have ingoing wave at the horizon. Again, I also showed in the previous lectures that this hypergeometric functions, at the end of the day, they reduces to plane waves at the horizon. So one was ingoing, the other was outgoing. So when we identified them, the ingoing and outgoing, we will just kill the outgoing wave at the event horizon, and we will stay with only, and we will just consider the ingoing wave solution as a general solution. Okay, so the one which leads to the ingoing wave, which is the first term, will be our general solution, physical solution for our quasi-normal modes. Then we will extend it to the spatial infinity. No, I made just a mistake because yeah, that was the outgoing. So this outgoing wave is killed, and we just kept the ingoing one. In the previous, as I said before in my lecture notes, that was explained in detail. So this C2 should be kept in order to satisfy the first boundary condition of general solution. Anyway, then we extended to the spatial infinity by using one of the hypergeometric transformations. That answers can be also found in yesterday's lectures. Anyway, so up to here is the common things that I do. So what is the new thing? Okay, look at here, we have eta, and this eta has omega. So this eta is also has a role of determiner of ingoing and outgoing waves. So this is ingoing because of its negativeness, and that is positive and that is outgoing. So we have to keep this, but we have to terminate this expression because we don't want any ingoing wave at spatial infinity. So how we can terminate? Because we have only one amplitude here, C2. We don't have two amplitudes, but we have two different modes. One is outgoing, the other one is ingoing. So if I kill the C2 that I did for event horizon, I will completely lose my wave. So to keep the C2, but to kill the ingoing wave, I am going to apply to one of the properties of gamma functions, which is called the poles of. I am going to use the poles of the gamma functions. So what is the meaning of the poles? When the gamma parameter, let's say sigma, if it takes negative integers, they lead to infinity. So if denominator seen here, if one of them becomes infinite, so this ingoing wave automatically will be terminated. So this is what we do. This is what I expressed here. Let's take the black. You see, this is the structures of the poles. If the Z takes 0 and negative integers, so 1 over gamma goes to 0. So by using this mathematical reality, I have two conditions. Either that C tilde minus A tilde is minus n, C tilde minus A tilde, because C is also written in terms of A tilde, you will get 1 minus an if you look at our hypergeometric solution. The other one is B tilde is the negative integers. So we will have two classes here. When you put these conditions, because each A and B, they also include omega. And if you make the omega alone, if you express it in terms of n's, you will see that you will have a quantized frequencies. And now it is complex. So these black holes are just decaying in time, okay? They are just decaying in time with that expression. So these are called the quasi-normal modes. But there is a condition here, because I like to look at here. Since we want it to decay in time, this omega imaginary should be also negative, because if it is positive, instead of decaying, it will grow in time. So that leads to instability. So the quasi-normal modes should not modify the stability of the black hole. So we are picking the negative ones. But in order to keep this negativity, the n should be greater than L. So the condition n is greater than L are purely dump modes, which indicates the space-time is stable under this kind of perturbations. But for n is less than L, scalar field perturbation is enlarged along the time, which shows that the rotating linear diameter is unstable. So only the n, these numbers, let's say quantum numbers, if it is greater than the orbital quantum number, we will have quasi-normal modes, which keeps the stability of the black hole. I mean, the black hole rings without, let's say, terminating itself. Okay, this is what we want. I mean, when you hit, let's say, perturb the wine, we don't want to break the wine glass. We just want to hear its voice. This is what we do. Only when the n is greater than L, we can get the pure quasi-normal modes with preserving the stability of the black hole without, how to say, terminating our black hole. Otherwise, such modes, I mean, when n is less than L, that shows instability and that, you know, how to say, terminate our black hole. This is also, I think it's shown in where as an experiment while the soldiers are walking on the bridge. So if, as you know, if it comes to its natural frequencies, the bridge can be collapsed. So we don't want to collapse the black hole. We would like to just get its waves because normally to have such ringing, characteristic ringing, we have to preserve our black hole. So this is how we can get it. I hope it's clear. But computing quasi-normal modes is not just from one method. Okay, I am now showing you the exact solutions. So how we can get the analytical quasi-normal modes. I hope you can get its logic or its methodology. The another powerful tool is the Wkb approximation. I will also give some details about this Wkb approximation because currently we are also using this technique because getting exact solution is rare in black hole physics. In many times you encounter with many problems while attempting to get its analytical solution of a wave having a different spin. So to overcome these difficulties, we apply to the Wkb approximation. I will give one of the popular methods described by the Konopoulia in the literature, and I will give its details to you in the next slide. The third one is also one of the good techniques. It is called monodromy technique. But it is, you know, for the highly damped modes. The highly damped modes means when n is too large, too great. And also we have a series solution, although we couldn't get the exact solution, but especially by using the Frobenius method, you can get some series solution, and that series solutions can be tabulated in tables. And it also works very fine. Also the resonance methods, I mentioned it in the previous slide, if you remember. For instance, when we force the Heron functions to be a polynomial function, automatically resonance frequencies appear, and they are also counted as quasi-normal modes, characteristic frequencies. And the sixth method is called the continued diffraction method. To have more details about them, I also referred the students to have a look at this topical review. This is one of the good review currently in the literature. And the authors are Berti, Cardoso, and Starenides. So they made a good topical review, and it was published in Classical and Quantum Gravity in 2009. There are some updated topical reviews, but to understand what's going on by that time, from the beginning of the quasi-normal mode definitions, this is one of the good articles that should be read. Okay, so I said you that I'm going to give some details about the Wkb approximation to have the quasi-normal modes. This time, we have, if you remember in our exact solutions technique, I was writing the one-dimensional Schrodinger-like equation as like this. But in the WKB, this effective potential should also include the frequency. I mean, you have, again, a one-dimensional Schrodinger-like wave equation, but you don't even need to separate the effective potential from the frequency. So just you bring your wave equation to that structure, okay? After bringing to that structure, we impose the boundary conditions with the help of the Tortoise coordinate. Yes. So what we will want, when R star goes to minus infinity, this is called event horizon. And this is when R star goes to positive infinity, this is spatial infinity. So at the spatial infinity, we would like to see outgoing waves, and near the event horizon, we would like to get just ingoing waves. Okay, so these are the boundary conditions that we should get. Okay. So what this Konopolya did, okay, he said that, okay, we will have a maximum potential at a specific point, let's call it R0. And then he split the problem into 3 regions. So in region 1, it is just from event horizon to the R1, and R1 is the first turning point where the potential vanishes. Okay. R2 is region 2 is from R1 to R2. R2 is the second turning point. Again, the potential vanishes. And the region 3 is from R2 to positive infinity. So there are 3 regions, okay? So what is the Tortoise coordinate? If you have a generic metric like this one, even A and B might be different from each other, not they're just F or 1 over F. For such a metric in general, the Tortoise coordinate is nothing but dr over dr star is equal to root AB d over dr. So from this combination, you can all the time get the star with a simple integration. And if you are lucky, you will get its analytical expression. So instead of Z, he used this exponential functional form. Okay, so instead of Z, he inserted that exponential functional form, and that Sn or Sj is just the function of the potential and its derivative. And all the details of this procedure was published in PRD in 2003 by Konopolya. Okay, and he derived the frequency as the 6th order with the 6th order treatment. Okay, that is the here. So its accuracy is very high actually. And that V0, as I said before, is the peak value of the potential, okay, when R is R max. That lambda J's also can be found in this paper, and he did for d-dimensional Schwarzschild black hole, but it works for other black holes as well. And the good thing is that he formulated everything in a computer package program of Mathematica, and it is also available in his website. So this is the website that you can find this Mathematica. Anyway, so this is a one of the important tool to get the frequencies, quasi-normal frequencies, because when we match it with our exact quasi-normal mode results, we see that there's a very high accuracy between the results. So that it's one of the best, how to say, methodology currently available in the literature. I mean the Wkb in 6th order. As I said before, it was done by the Konopulya, and we are currently also using it whenever we couldn't get the exact solutions to the wave equations. Anyway, up to now, I showed only the spin zero particles, spin zero fields for you. But as you know, there are other spin fields. One of the most popular one is the spin half. And as an example of spin half particles, electron, for instance, neutrino. Zoom prevents me to pick up the choices of the pen. So these are for spin half. So electrons, neutrinos are the good samples for spin half particles and their corresponding fields. But now I would like to show you how we can get the quasi-normal modes of fermions. With fermions, this is what I mean, the particles having spin half in 4-dimensional curved spacetime. Of course, we should follow the Dirac equation, but what is the Dirac equation? It's in its form seems complicated. I mean, if you use the Pauli matrices and etc., really its structure makes the students very or the students experience very hard times to derive the Dirac equations for a given curved spacetime. So the easier way is to follow the Dirac equation in the Newman-Penrose formalism. So this Newman-Penrose formalism is a tetrad. It's a complex null tetrad formalism, actually. There are some conditions. We will have 4 null vectors. These are called Li, Ni, Mi, and its complex conjugate M bar I. And there are some relations between those null vectors. So if you make a scalar product between L and M, L and M bar, N and M, N and M bar, you should get 0. Okay, and similarly, if you multiply each null vector with itself, you should again get 0. However, if you make a scalar product between L and N, you should get 1, and M and M bar, you should get -1. Anyway, so this is the fundamental matrix represented by eta AB in a symmetric matrix form, and our Newman-Penrose formalism is based on it. Anyway, so how you can test that you have the correct null vectors? The contravariant form of your metric tensor, if it matches with that combination of the null vectors, okay? So that means, and the previous conditions of L scalar N is 1, M scalar product M bar is -1, if they hold, plus if you can get the contravariant form of your metric tensor like this, okay, with after this combination, that means you constructed your tetrad. So, and also the covariant form of your metric tensor can be obtained like this. Okay, so the orthonormal tetrad, so as I said before, the null basis vectors are based on the eta matrix with the orthonormal tetrad field. Anyway, so once we get them, we will find the spin coefficients. These spin coefficients are related with some geometrical properties of your curved spacetime. They are related with, let's say, shear, twist, rotation. So their meanings also can be found in the book of Chandrasekhar. You can look at the Chandra's book, the mathematical theory of black holes. Anyway, but we have 12 spin coefficients. Again, they are obtained from the tetrad. I mean, those null vectors, L, N, M, and M bar. And also we have directional derivatives. These are also defined. As you see, the capital D is Li and times this operator, and small delta is related with Mi. Capital delta is related with Ni, and the delta bar is related with M bar. Anyway, so with that tetrad formalism, the Dirac equation is written like this. Here we have also, if your space-time is charged, I mean, if it has its own electromagnetic vector potential, we can also put the charge to the Dirac equation with this with those expressions extra. If the Q is because the charge of the fermion, but if the space-time has not any electromagnetic vector potential, that term goes. So it's not important to put the Q here because it will be gone. So you see these epsilon, rho, beta, tau, these are all spin coefficients. In the Dirac, we will have 4 different spinors. These are capital F1, F2, G1 tilde, let's say, and the G2 tilde. And the right-hand side here is 0, but if you have massive case, instead of 0, you have to put I mu P. So this mu is the mass of fermion. But massless cases are very, very hard comparing with the massless cases. Massless and charge are much, easier. But adding the mass to the Dirac equation can increase the difficulty of the problem. But if you can add and if you can get its exact solution, of course, it will be much, much valuable. As I said before, the Q is the charge of the fermion. Each A, the callipratic A's are the jade components of the vector potential of the background electromagnetic field. Okay. However, when we have static space-times, I mean, they are independent of time, and if it's independent of phi, cyclic coordinate, in general, keeping this exponential is logical, and each F1 can be, each spinor can be written in terms of radial and angular parts. Okay, so this is what we do. Here K is frequency. Here I quoted it from one of my old paper. So K is nothing but omega. Okay, it's not different than our omega. Let me just make this omega better. Okay, so K is the frequency of the incoming wave, and M is the azimuthal quantum number. The temporal and azimuthal dependence are chosen to be same, but the axial and angular dependence are chosen to be different for different spinors. So these are the spinors. These are the, how to say, the wave functions which are waiting to be solved exactly. Okay, then, just as an example, as I did before, we have one charged linear dilaton black hole solution with two horizons. Over there, we had a vector potential. We had a vector potential, including a magnetic charge. Okay, so that is our background. The B, metric function B, as I said before, it has two horizons. R2 is event horizon and R1 is the inner horizon. The B is constant. The R is the coefficient of spherical line element. A is constant, A squared times R. So that was one of our old paper, but now I would like to use it to get the exact solution for the fermions. Okay, so the R1 and R2 are expressed in terms of the theory's parameters, because this black hole is the solution of Einstein-Maxwell-Dilaton theory having the double Liouville type potentials. Okay, next. So this is our tetrad. Okay, so how I am sure that it's the correct tetrad? First, I checked, as you see, their the null vectors, scalar products, and I am sure that L dot n and minus m dot m bar is 1. So it works. If you can check it, you will see it. The next is I also checked whether it gives me the correct metric tensor, and you will see that it gives. So after become sure that everything is okay about my tetrad, I compute the spin coefficients. The non-zero ones are obtained like this. Rho, mu, epsilon, gamma, alpha, and the beta. The only non-zero ones are those spin coefficients. Then I insert everything into the Dirac equation that I shown in the previous slide. And at the end of the day, you will get 4 different equations. Here, Z tilde, L dagger, these are all operators, differential operators, like, yes. So the radial operator is appeared like this. A was, if you remember, it was just a constant for R function, capital R function. Here we have lambda, the lambda is this one. Here we have H is that one. And the angular operators appear in that structure, okay? Where the P, if you compute it correctly, you will see that just after the half, you will have QQ parameter, and we call it now P. Now, Dirac equation has a high symmetry. As you know, there is a hypothetical Dirac C. So the positive and the negative fermions, actually, they obey the same mechanism. So there is due to that high symmetry, those 4 equations reduce to 2 equations, for especially the radial equation. So in general, just the structures of the radial and angular equations are very similar to each other, and especially, and also if you do F1 is equal to G2, F2 is equal to G1, this is the high symmetric outcomes of the Dirac equation. You will get that, how to say, reduced or most simpler Dirac equations. So this is called the radial master equation. Similarly, the angular master equations will be like this. So our aim is to find what is G1, what is G2, A2, and A4. Because if I find G1 and G2, we will automatically find F1 and F2. Similarly, finding A2 and A4 will also correspond to the solutions of A3 and A1. Anyway, so these angular equations are very historical, actually, equation, because our black hole is spherical symmetric, and that was studied much before as spin-weighted spheroidal harmonics problem. Okay, so this is the spin-weighted spheroidal harmonics system. And now our L dagger and L with A2 and A4 are matching with that structure. So this is the definition of spin-weighted spheroidal harmonics. S is its weight, spin weight of this spheroidal harmonics. Anyway, when we compare them, we see that A2 is obeying this one, belonging or matching to -1/2 plus P spin weight, and A4 is this one. So actually, we get this solution automatically, and it has eigenvalue. And if we compare the eigenvalue, its eigenvalue now for our case is this one. L square should be equal to L plus half square minus P square. We also get the eigenvalue now from the angular equation. And over there, a condition automatically appears because 2P should be N in order to satisfy this spin-weighted spheroidal harmonics. And this is called Dirac quantization rule. And we see that Q times Q should 2 times Q times Q should be an integer. And this is, as I said before, is known as the Dirac quantization condition. Anyway, so the main contribution of angular part for us is to get the eigenvalue. Now we got the eigenvalue, but my all problem is, and in general, to get the radial equation. So to have the radial equation, we first look at also its one-dimensional Schrödinger-like potential forms, because I would like to also get the potential form of this curved space-time for the fermions. So to this end, I redefine the G1 and G2 with capital G1 and capital G2 with a scaling factor 1/a times R times lambda to the power of 1/4. So that makes my radial equations much more simpler, okay? Then I also define the tortoise coordinate, which admit exact solution. So by this way, we get a much better radial equation, much simpler. You see, many now terms are gone. So after that, this is also what the Chandra did. You have to redefine G1 and G2 with two other functions like P1 and P2, and this is called addition and subtraction method. So when you apply this addition and subtraction method, you will exactly get one-dimensional Schrödinger-like wave equations, which are obeying this condition. So here J is just a subscript. It is a generic one-dimensional Schrödinger-like wave equation. It is also called Zerilli equation. This is also called the Zerilli equation. I mean, that one-dimensional Schrödinger-like wave equation's other name is the Zerilli equation. It's original because the Zerilli has a similar studies in the past. And when someone works in Tortoise master equations, this Zerilli expression automatically, say, repeated over there. Anyway, so here we have two here one-dimensional Schrödinger-like wave equation. So J is varying here from 1 to 2, okay? And the effective potentials can be written. Here I have -1 to the power of J, because this sign is can be negative if J is 1, and it is positive if J is 2. So here we have two effective potentials, V1 and V2. Then I check, because what I know, at the event horizon, effective potentials should vanish, and it is. The both V's are vanishing at the horizon, because the B R plus was 0, because my metric function was vanishing at the horizon. And at spatial infinity, we have a barrier. This is normal, it might be. So this is the near horizon potential, and this is the asymptotic potential. So if we draw V versus R graphs, you see they are vanishing at the event horizon. When we increase the orbital quantum number, by the way, the V values are getting higher and higher values. So the barrier is increasing with the increasing of L number. Anyway, and near the horizon, we have this kind of solution. Automatically, G1 and G2, which was the combination of P1 and P2, they also admit plane waves, ingoing and outgoing plane waves near the horizon. So everything is fine. Yes, but what I want, if I want to get the quasi-normal modes, all the outgoing modes should be terminated. So these are D3 and D4 are terminated with terminating the coefficient. So we have to just get the D1 and D2 solution, because D3 and D4 are belonging to the outgoing waves. So we don't need them. So therefore, the generic G solutions near the horizon is this one. Okay, and also at the asymptotic region, since R star, tortoise coordinate is like that, we have such a structure at the asymptotic region for R star. This is yes, I express, so I'm repeating it here. Okay. Where this alpha tilde, by the way, is just eta over P, and yes, exponential imaginary eta R star can be written like this. So at the asymptotic structure, we have again plane wave structure, but this is purely outgoing wave. So what I am sure here, my solution is in the correct way of getting the quasi-normal modes. But I would like to find the exact solution. This is what I am going to do. So this is how to say approximated solution by using the limiting cases of our potentials near the horizon, and this is the near horizon, and this is the asymptotic solution of our G's at the spatial infinity. But as I said before, I would like to get the same characters by getting the exact solution. I'll take some water. So when I decouple, because if you remember, we have two equations, and in each equation, G1 and G2, there's a system actually. We have two sets of differential equations. In each equation, we have both G1 and G2, okay? So if I am going to write, let's say, get G1 in terms of G2, then insert it to the, let's say, to the first equation, and get one equation for G2, and later on one equation for G1. This procedure is called decoupling. So if I decouple the equations, I will get second ordered two differential equations. So again, J is 1 and 2. So we will have two second order differential equations, and they are in decoupled form. For instance, in this decoupled forms, if we take the limit of spatial infinity, we will get again ingoing and outgoing solutions that we obtained from the Radial equation. But this is coming from the decoupling, okay? So, and again, the ingoing one should be gone, because at the spatial infinity, we want purely outgoing wave at the spatial infinity. Thus, this C is not important. Anyway, so we can get the, how to say, also the plane wave solutions from the decoupled equations. But how about the exact solution? And that is the problem. So since I have decoupled equations like this, again, I insert another function, let's call it H. And also I am changing my variable. So this is the experience that we obtained from the Klein-Gordon equation. So we know that such transformations can help us to find the exact solution. So after inserting this G transformation, and then if we change the variable from R to Z, okay, we will see that we get another hypergeometric differential equation. So that two actually decoupled equation, because J can vary from 1 to 2, can take 1 and 2. Don't forget, it seems one equation, but actually it's two. But this is a good technique to have to say unify the decoupled equations to a one equation. So I can get A, B, and C. These are the variable, the parameters of the hypergeometric differential equation. So you see, I have two coefficients, but we have to be again selective, because when I get its event horizon limit, the one which admit the outgoing wave should be terminated. Yes, and the other A tilde, B tilde, and C tilde, which can be obtained from A, B, and C. These are standard things. So as I said before, when R goes to R2 event horizon, R star goes to minus infinity, and then Z goes to 0. And we know that hypergeometric functions variable, if it is 0, we get 1. So that we get ingoing and outgoing plane waves at the horizon. And each time we have to kill the outgoing one. So G2 is expressed in terms of C2, G1 is expressed in terms of C1, okay? Because we have two G's, and since, let me turn back. Yes, here I have HJ, but this HJ is going to be multiplied by this factor. So therefore, for the outgoing wave, let's say for G1, can be ingoing wave for G2. That's why for G2, I am keeping C2, but for G1, I am keeping C1. Anyway, so this is that. So this is my general solution, physical solutions for G2 and G1, which will help us to get the quasi-normal modes. So since Z is proportional with or directly related with R, so when I transform this solution to the spatial infinity, I should look for 1 over Z transformation, because again, I want the hypergeometric functions variable to become 0 at the spatial infinity. This is what I do. Okay, when R goes to 0, 1 over Z goes to 0. When R goes to infinity, sorry, 1 over Z goes to 0. So this also makes me to find the G1 and G2 solutions at the spatial infinity. Okay, but here, as I said before, these factors, again, will make a distinction of, and here, we'll make a distinction of ingoing and outgoing waves at spatial infinity. However, we want only outgoing waves at the spatial infinity. Yeah, and this is what we got. Okay, so one of them is this is outgoing, this is ingoing. Similarly here, this is out and this is in, but we don't want the ingoing ones. So how I can kill them without killing the C1? Because if I kill the C1, I also kill the outgoing. So this is not the way to terminate the amplitude. We have to terminate the gamma functions by using their pole structure. By using their pole structure. Yes. So so these poles, this is what I say, D1 tilde is this one, D2, I just tabulated here. So what I want to do to make the D3 and D4 0, but to this end, I will use the pole structures of the gamma functions. So what does it mean? Look at the D3, A tilde and C minus B must be 0. And here also A and CB must be 0. Okay, but in each one, I can get the K, which is the frequency now. You don't forget the K is now my omega, just definition. Okay. Then we get a table. Meanwhile, we have the beta formula. This beta formula should be greater than 1. I think it is because of positivity somewhere. It's most probably it should be like this. Yeah, most probably, yeah, here. And it's something should keep the positivity of K. But since, yes, we have to find stable, and we have stable and unstable modes depending on the positivity of K. And we all tabulated them here. If the K is, because it was something like this, exponential, if I not remember, it was IKT. So we should find the K as positive. I mean, imaginary K should be positive. This is what we do. So this is the ones which gives us positive Ks. And these are the ones with negative Ks. Because if the imaginary K is negative, exponential will be more positive. So that means growing modes. Growing modes causes unstable modes. And similarly, we got the quasi-normal modes for G2. So these are all coming from those equalities that I obtained here. I mean, that will give me the quasi-normal modes. In each time, I will make the K alone, and I will make the K as a function in terms of n. Okay. So we can get the exact quasi-normal modes. And the last part that I want to talk is about the black hole quantization. This black hole quantization actually is related with the electromagnetic radiation. So what we learn in modern physics if you remember, if we have an electron, if it is transit from higher energy level to the lower energy level, what will happen? So this energy difference will show itself as a radiation, okay? So the difference in energy will cause the radiation. The similar thing can be made for gravitational radiation. If there's a quantum transition from higher energy to the lower energy, automatically a kind of radiation should be made. So this is called the gravitational radiation. So we can use this analogy to show that our black hole is quantized, because the similar analogy, the similar logic was applied for the atom, and at the end of the day show that energy is quantized. If you remember the Bohr's atom model. So that will be our approach to show that whether the black hole is a quantizable object or not. I mean, while it is shrinking, is that shrink, or maybe it is also enlarging while its sizing is getting larger and larger? Is the continuous growing or continuous shrinking, or it's a quantized shrinking? That was the question actually was asked by Bekenstein. According to me, maybe after the Hawking, one of the major contributor to the quantum gravity is this guy. Anyway, so to understand the quantization, we have to remember some important terminologies like adiabatic invariant. What is the adiabatic invariant? It's a physical quantity that is almost constant when changes are made very slow. Maybe in thermodynamics, you know this adiabatic process. In the adiabatic process, if you remember, adiabatic process, what was it? The Q was 0. I mean, the change in heat was 0. So this is something like that. So this is the definition. We are making some changes, but the physical quantity will become almost constant, okay? Then the Ephraim created a theory. He said that any classical adiabatic invariant corresponds to a quantum entity with discrete spectrum. So if we have a adiabatic invariant, it should admit a quantum spectrum. Then Bekenstein in 1974, this is Chandra, this is Ephraim. Then in 1974, the Bekenstein showed that the black hole horizon area can be regarded as an adiabatic invariant. So while, let's say, there is a very, very small change, let's say our black hole is swallowed matter, its horizon area, the change in its horizon area is almost 0. I mean, the horizon still is a constant quantity, so that the horizon area can be seen as an adiabatic invariant, and he made an Gedanken experiment. I will mention this Gedanken experiment in the future slide, next slides. But also let's remember what was the Ephraim principle. In the case of radiation, the invariant quantity is energy over its frequency. So this, please keep it in your mind. because later on, whatever I do will be related with this Ephraim principle. Anyway, and at the end of the day, in adiabatic invariant quantity, if you have an adiabatic invariant quantity, it should obey the quantization, and this is called Bohr-Sommerfeld quantization rule. So if I have an adiabatic invariant quantity, it must be quantized according to the quantum physics, and this is how the Bohr actually quantized the atom. Anyway, what the Bekenstein did, you may check his papers. The famous one is that he published in 1974, and it is called Quantum Black Holes as Atoms. And also he published another revolutionary paper as Black Holes and Entropy, and he became very, very famous about that paper. So what he did over there, and what was the question? What is the minimum change of the horizon area in the process of assimilation of a test particle with charge E falling into a black hole of mass m, charge q, and angular momentum? So he asked this question to itself, and he made two approaches to this question. One is the classical approach. Okay, the area of Kerr-Newman solution, because this black hole, which has a charge, rotation, charge and rotation, is nothing but the Kerr-Newman solution, and that is the chemical potential, which is defined in terms of the charge. And now we suppose that it is now absorbing or swallowing an a particle, okay, with charge epsilon. So then he took the change of the area. Okay, when the area changes, the mass will change, the charge will change. Okay, and okay, he said that, okay, what is the amount of change of the black hole charge if it swallows a particle with charge E? It should be the same. So the charge of the particle will be nothing but the change of the black hole charge. And similarly, the energy, which is now its mass of the black hole, is nothing but charge and chemical potential. Anyway, when he inserted everything to here, okay, he saw that, okay, the change in the area must be zero, but this is a classical approach. So he said, okay, classically, the area is an adiabatic invariant quantity. Then these two guys, Christodoulou and Ruffini, by getting inspired from the Christodoulou and Ruffini's paper, again, the Bekenstein, this time he approached the problem quantum mechanically by using the Heisenberg uncertainty principle. And at the end of the day, he proved that the minimum change of the black hole area is nothing but 8 pi epsilon h bar. This epsilon is the order of unity, so it is just 8 pi h bar. So the minimum change of the black hole will be 8 pi h bar. So this is called the Bekenstein conjecture, and after him, there are many studies on it. Okay. So, and also, this is the minimum change. So, and the area should be quantized. The quantization, meanwhile, the LP square, I mean, the Planck length square is h bar, keep in your mind. The quantization of area should obey this rule. The alpha is an undetermined dimensionless constant, and so from black hole to black hole, it might be vary, but at the end, the quantization of area should be related with h bar. Anyway, then in this subject, one of the important steps came by the Shahrar-Hot in his PRL paper in 1998, and then in his PRD paper. What he taught, he suggested that this alpha can be determined by utilizing the quasi-normal mass frequencies of an oscillated black hole. He redefined the Bohr correspondence as a transition between the levels. So the transition between the levels is nothing but the black hole quasi-normal modes. So as I said before, when there's a jump from high energy to the lower energy, there will be radiation, and this transition should be the quasi-normal modes. This is the what Hot suggested, and the Hot used the Knoller's paper, and he used its frequency. Then what he did, he said that, okay, the change in the area, it should be 32 pi m times delta m. So how he did it actually, look, I think we can see it here. The area is normally pi r plus square. What is r plus? R plus is 2m. So r plus square will be 4m. I'm talking about the Schwarzschild, of course. So the area will be 16 pi m square. I am going to look at the change. It will be 32 pi m dm. Okay. So instead of the m, this is what he is using. Okay. And at the end of the day, he proved that, okay, the area will be quantized like this one. Anyway, later on, in another PRL paper, this is the Kungstatter paper. It was published in 2003. He said that, okay, he used the Ephraim principle, because if you remember, Ephraim principle, it's for saying that this ratio should be adiabatic invariant. So he used, okay, the energy and the frequency, and he defined it as I. And now this frequency, if it is quasi-normal mode frequency, okay, and he said that, okay, I will get the quantized area again, and that was the Hot's value. So he redefined the Hot's value by using the quasi-normal modes, real values. Later on, Maguire, he said that, okay, but the frequencies is made, I mean, the quasi-normal frequencies are made by real and the imaginary numbers. And in general, the damping of quasi-normal modes are dominant comparing with the oscillation. So he said that if I am going to consider the highly excited quasi-normal modes, omega I will be dominant. So instead of real numbers, he used the transition of damp modes. Okay, he used the transition of the damp modes, which the transition means the transition between the neighboring states. If we use the quasi-normal modes and take the neighboring transition, for a Schwarzschild case, it will be 1/4 pi m. And then he used it, he put it here, okay? So what we get 4m dm at the end of the day, okay? And then he equated the Bohr-Sommerfeld quantization rule, and he proved that the area is quantized as the Bekenstein's offered wave, which is 8 pi LP square n. So that LP is just the H bar, as I said before. He obtained the Bekenstein result by using the quasi-normal modes. And then he checked it. With a classical test. So the change in the mass energy is nothing but H times the transition frequency. And then he put it into the change in the area, which was this one. So instead of delta M, he used H bar delta omega. When you insert it over there, he got the same answer, which is 8 pi H bar, or 8 pi LP square. So that was also make a revolution in black hole quantization. After that, Magyar's methodology applied to many black holes, and they derived the black hole quantization by using the quasi-normal modes. Anyway, I have 4 minutes. I am aware of the time. Let's apply it to our solution. As I said before, we got the frequencies like this. So we are going to consider the highly damped modes. I mean, we will take the n higher. So when we get the n higher, okay, this becomes dominant, this term, okay? And here, even half is not maybe important. 1 over R0 is related with the surface gravity of the linear dilaton black hole. Then we find the transition between the 2 modes. So n minus 1 to n, or n plus 1 minus n, it doesn't matter. You just look the transition of 2 frequencies. And at the end of the day, you get again the surface gravity. Okay. Yes. Yes. The reason is this one. Now here we have 2 classes actually. That's why that is the quasi-normal modes 1 minus an. But we have another class that I didn't drive it in the previous one, because the gamma poles can be achieved in two ways. One of them was Cn minus an should be minus n. The other one was Bn minus n. However, if you go from the derivation of omega from here, the obtained omega was very complicated. It's lengthy. But in the case of large charge and low orbital quantum number, yes, in the case of this one, we prove that the quasi-normal modes will appear in this structure. And when you go to the transition frequency, you will get exactly 2 pi th over h bar. Okay, here, because I didn't suppress the h bar to 1, I didn't use the natural units. I kept the h bar as h bar. Then if we use the adiabatic invariant quantity, because energy, it was T times ds. That is the energy should be used in radiation, because, and the adiabatic invariant is T times ds over transition frequency. If you insert this transition frequency here, okay, if you insert this transition frequency here, and you will see that the h will cancel to each other, and this is equal to the nh bar according to the Bohr-Sommerfeld quantization rule. Anyway, yeah, this is what I show you. It will be h bar as, this is the black hole entropy over 2 pi. You got R2 over R0 over 2 will be in h bar. And as the entropy for our black hole is nothing but the quarter of the area. Once we put R2 times R0, once we express the R2 times R0 in terms of black hole area, we show that this is the quantized area, in other words, quantization of the black hole, and the minimum change in the area is 8 pi h bar, which shows that the spectral...
Just a reminder that we are running out of time.
1 minute, please, and then it will be gone, finished. Then we show that the minimum change in the area is 8 pi h bar, and this is exactly what the Bekenstein got it. So our rotating linear dilaton black holes also follow the Bekenstein conjecture, because the obtained result is independent of the black hole parameters like the rotation. Because this is a universal, the minimum change of the area of the black holes are independent of black hole parameters. And this is what the Bekenstein offered in his original work. Anyway, these are the things that I would like to share with you. Mainly, I try to show you that if you can get a exact analytical wave equation for a curved spacetime, of course, those curved spacetimes that I am using are the black hole spacetimes. We can use this exact solutions to derive Hawking radiation, gray weather factor, quasi-normal modes, and also by using the quasi-normal modes, we can also work in black hole quantization. Since we have exact solutions, I believe that the things that we got are much more reliable and more reputable according to the view of peer reviewers. Thank you very much, because I would like to stop here. I don't want to exit my time too much. If you have any questions, I am ready to receive them.
Thank you so much for this beautiful lecture, sis. It's been great for all of us. Let me start the recording first, and we may get questions if we have any. Just a second.